Yeah, thank you. Thank you very much for introduction, and also thanks to the organizer for giving me this opportunity. Yeah, and yeah, as a representation theorist, I always kind of admire some research and intuitions from physics. So it is really kind of an honor for me to have an opportunity to give a talk in this mathematical physics conference. So yeah, as this title said, I'm going to talk about some relations between representations of some quantum groups and also some notion of the vertex algebra, and in particular the W-algebra. So these two are actually coming from the well-known semi-simple finite-dimensional complex Lie algebras, but these two are actually quite different algebraic structures, and also they also kind of represent some different physical contexts or phenomena. But sometimes it happens that there are some relations or connections between these two topics, I mean vertex algebras and quantum groups. And if it happens, then it usually means that there is some deep connection or meaning in this physics literature. So I mean, many of you have already known about some, for example, Cartan-Lustig equivalence, which is probably now interpreted by some kind of holographic in mathematical physics, but this topic is also has some different natures, but probably it is not very popular for people, even for mathematical physicists. So I would like to choose this topic for today's talk. Okay, so let me begin from some classical results. And I'd like to go first from the user finite-dimensional semi-simple complexity algebra. I'm always working on the complex field, so you don't need to bother with this field, base field. Then, its representation theory is usually already well known. These are irreducible high-weight representations. And to understand or investigate these high-weight representations, one common tool in the representation theory is to consider some center of this algebra. More precisely, we have to consider the center of universal enveloping algebra. But usually the center of the algebra is very hard to, has some complicated structure or hard to describe. But in this case, it has a very nice description under the famous Harish-Chandra-Holm physics. So this says that the center can be identified inside some very easy Lie algebra, which is the so-called Gartang subalgebra of this Lie algebra G, and this is the universal enveloping algebra of Gartang subalgebra. Since this is Gartang subalgebra, it's abelian Lie algebra. This is just a symmetric algebra. So this is a super easy algebra, and inside this, you identify the center as some invariant part, which in this case, which is under the Y group action. And finally, this invariant subalgebra is actually studied from almost, I don't know, almost 200 years ago. So anyways, and this algebra is now known to be isomorphic to, again, a super easy algebra of, namely the polynomial algebra, with respect to some invariant, fundamental invariant polynomials. Yeah, so this is very, very well known. And next, I'm going to the affine case. Now we consider G hat, which is defined as the, we're taking the loop algebra of this finite dimensional algebra, and we take the central extension. Yeah, and we similarly consider its highest weight representations, which looks like this one. And here we have two differences from these finite dimensional representations. If you are not very familiar with these affine algebras. So namely, the first one is we have extra parameter k here, and this k is a so-called level, which is level k, and this is the eigenvalue of the central element C. So to study these representations of affine algebras, it is natural to gather these irreducible representations in terms of their modules. So it is more natural to consider something like this. So we pick some level k and we consider corresponding irreducible representations. And the second one is that this some general element or generator of this affine algebras looks like something like A tensor T to the N, where A is an element of G. But it is more natural or helpful to study this action of affine algebra as the some kind of field. So better to consider field. In this case, which is defined something like, given some element A of G, we gather these kind of elements in this way. So A tensor T to the N, G to the N minus 1. So this is kind of represents some fields in the two-dimensional theory, and also some calculus between these fields, something like normal order products or some OPs. So these two differences says that we had better to consider this representations of affine algebras as the so-called vertex algebra representations, or in this case, affine vertex algebra, which is defined written something like this, and we consider this. So this is kind of correct framework to understand the representations of affine algebras. Okay, but then can you apply some similar strategy to understand the representations? Namely, we may consider some center of this affine vertex algebras, but unfortunately, it is 0. Yeah, so it is not really, the center is not really useful to understand representations, but there is exactly one exception, namely when k is equal to some specific value, which is called the negative of the dual Coxeter number, which is also called critical level. But actually, these representations of affine algebras has very, very interesting things outside the critical level, but let me focus on the critical level today, because in this case, we have this center, critical center, has the very interesting structures at the critical level. Let's just write this way, G hat, which denotes the center of the, well, I'd like to write V to the minus H check G, but for some technical reason, let me just write. You can just, you can just read this as some kind of just vertex algebra at the critical level. But anyway, now this center is, we can actually do very similar things with this realization of this center in the finite-dimensional case. Namely, we can again consider this center inside some very easy algebra. Again, this is some kind of Gartang part of this affine algebra G, and from the perspective of fields, this represents the algebra of the free fields. So this is a free field algebra. So as its name suggests, this free field means that there is no interaction between these fields. So this, for example, these OPs are very, very easy. So this is again very super easy vertex algebra, and again, this center can be understood as some invariant part of this free field algebra. But now in this case, rather than the group action, there is some operator called the screening operator. Screening operator. So that this center is described exactly as the kernel of this screening operator. So when G is rank n, there are n screening operators, and this is isomorphic. Okay. Yeah, but if this is really parallel with this finite-dimensional case, then we can also expect that this kernel of intersection of kernel screening has some other realization or meaning, and this is indeed true, which is related to a very important result by Fagin in Franke, that these kernel screenings or centers are actually the same as the so-called classical W-algebras. Sorry, we have to put net yours here. I cannot give definition of this classical W-algebras because I don't really have the time, and also I'm not really expert on these things. But this actually this is defined first by Greenberg and Sokolov, and this is kind of used to understand some classical integrability, and this is kind of best generalization of the so-called Virasoro algebra, for example. So this is kind of represents some extended symmetry in the two-dimensional conformability theory. Sorry.
K is equal to U minus A.
Not exactly the same, but kind of essentially the same. I mean, so basically this is an algebra of fields, and this is kind of algebra generated by the coefficients of the fields. So this is some technical part, but to explain the q-deformed picture, I need this term. So yeah, I'm a bit sorry about this. I mean, I haven't given any definition, and probably I won't today. So yeah, but feel free to ask me if anything is not so clear. So okay, yeah. So yeah, so this means that the center of critical this affine vertex algebra at the critical level and the classical double algebras are the same if we put these two things in this very easy algebra. So I mean, so this morphism should be called some kind of free field realization, and yeah, and this free field realization gives us an identification of this two algebra. Well, and yeah, of course, this isomorphism is very, very important things. For example, this is used. Well, I'm not really understanding the things, but this is crucially used in the formulation of geometric Lagrange correspondence by Bellins and Greenberg. Yeah, but today to comparison with the Q picture, I would mention another application of this correspondence that from this identification we can obtain some Bethe ansatz formula, whatever it is. This is some formula which describes some spectrum or eigenvalue of the Hamiltonians of some quantum integral models called Grothendieck model. So basically, this Grothendieck model is defined as the Hilbert space is some representations of this affine, finite-dimensional representations of this affine algebra. And if you, by this identification, this, again, this, the Hilbert space is carries the action of the affine algebra, and from this center we obtain Hamiltonians and also some commenting operators with Hamiltonians, which can be said some kind of source of this integrability. And from this identification with the classical double algebra, we can kind of use this well-known structure of classical double algebra to understand the, for example, to solve this Bethe ansatz, for example. So this is so again, Franke. Oh, I forget to write the year, but anyway, yeah. So this kind of correspondence between the integral model, namely the Grothendieck model, and also some ODE, because this classical double algebra can be defined as some kind of algebra functions on LG opals, which is mentioned yesterday, which is also related to some kind of differential equation. So this is also now understand as some correspondence between ODE and IM, integral model. But yeah. Okay, so this is classical results. And these things are done in 1990s and around that period. And I would like to move to the Q results. So these at these 1980s and 1990s, it's also a kind of period where when the so-called Q diseases are everywhere. I mean, these Q diseases are kind of some disease. And if you caught that Q disease, then the first symptom is that one day you found out that most of your mathematical results are actually admit some Q deformation. Yeah, this is a quote from some introduction of some textbook. Yeah, but I know. Well, I mean, you already seen some example in the yesterday's talk. Even in the random matrix theory, you can see some Q analog, right? So, and in this case, I would like to claim that everything here, almost everything can be reproduced with this Q analog. So we first have to begin from quantum affine algebra. Let me write it this way. So this is so beginning from this affine universal enveloping algebra or affine algebra at level K, we can consider the Q deformation. This obtained by Drinfeld, and it is also known that it has some presentation so that it can also yield some kind of description in terms of the fields. Except that we do not have some proper axioms to understand the calculus between these Q fields, but anyway, it is still possible. And then we can now consider its centers and representations. Now we consider this q-deformed center, which is again defined as the center of this critical level quantum affine algebra. Well, then, indeed, you can realize this center of this quantum affine algebra inside, again, some very easy algebra, which is, again, the q-deformed of this free field algebra or q-Heisenberg algebra. Okay, so. And inside this, you realize this image as by some, again, introducing something called q-deformed screening operator. So this is again identified as this one, where screening operators again act on this q-deformed Heisenberg algebra. So this is enlist isomorphism in type A. And it seems that people are not really interested in to extend this to any case, but anyway, yeah. And then this is basically for constructed for type A by Awata Odake. GIC 94. At least for this embedding to this free-field algebra. And then now Frankel Leszczykin introduced these q-deformed screening operators for general affine algebra. Yes. Sorry, Sam.
Conventionally, screening operator corresponds to pi projection.
Oh, well, yes. Yeah, affine version of pi group action, but yeah, but it is not the same. I mean, for example, this is not invertible, so this is not some group element, but still this can be seen. Yeah, this can be seen as some kind of linear term of the pi group action, in some sense. Mm-hmm.
Zero means level 0.
Yes, level 0. Right. Yes, right. Yes. Yeah, that's a very good point. There occurs some shift in the level by the critical level. I'm not sure I can explain conceptually, but I can say that it already happens in this finite dimensional case, because when you consider this algebra isomorphism by Higgs-Chandra map, you have to consider the shift by the file vector rho, right? So yeah, so it corresponds. Yeah, so this critical shift is also related, but yeah, there is some, yeah, yes, but and there is some geometric meaning I cannot remember, but yeah, if you are really interested, then you can Google it. There is some mass overflow question on that, exactly on the matter. So yeah, you can see the answer there. Yeah. Okay. Yeah. Yeah, and yeah. And by introducing the corresponding this q-deformed screening operators. Now, Frankel and Restikin defines the q-deformed classical W-algebra as formerly just as the intersection of the corner of screening operators. Frankel, Restikin. And also this connection with this integral models still hold at this Q after survive after this Q deformation. So from this embedding, you can also obtain observe some Bethe-Ansatz formula for spectrum of Hamiltonians of now something called Heisenberg XXZ spin chain models. So this Heisenberg XX spin chain model is exactly some kind of Q deformation of this Grothendieck model. So even at this integral model level, this Q analog there can be done for this. Yeah, it is physics level. Yes. However, I don't think that you are persuaded these Q things because, well, this Q deformation of, for example, classical W-algebras defined quite in some ad hoc way, right? Originally, there was some nice definition of this classical W-algebra in terms of some Hamiltonian reduction, but this is just defined as the corner of screening operators. But still, I would like to claim that, claim that this is not all. And at the Q, after this Q analog, we obtain a very some kind of new phenomenon with and also new connection with the representations of quantum affine algebras. So, so basically the idea is that, this is Frankel, Restikin, and 96. And and Frankel and Restikin noticed that if you see this Bethe-Ansatz formula for this type A case carefully, then this formula really looks like some kind of character of some representations of quantum affine algebra. So for example, the terms of this, the eigenvalues actually has some, the number of terms are actually the same as the dimension of certain representations, and the kind of the forms of each terms looks like that from some highest term you get go down by some kind of simple root. So this looks like there is some character, and Frankel and Restikin indeed make this observation as a precise theorem by introducing this kind of connection. So, so we consider the cross-ending ring of the category of some subcategory of finite-dimensional representations of quantum affine algebras, and from this. Frankel and Restikin define some map to the center of that critical level, so GQG head, by using the so-called transfer matrix. Yeah, this is also appears in one of the yesterday's talk, but I just let me just mention that this comes from the so-called universal R matrix of the quantum affine algebra. And then if you free field realize this as a free field, like the description by corner of screening operators, and everything is isomorphism and is at the type A case, then this map is really plays the role of the character, so-called Q character. And and indeed, it really looks like a field. So for example, if you begin from some representation here, then the image of chi cube V is not just some coefficients, but this can be really gathered into some fields in this for this q-deformed free field algebra. So this is.
Is there an isomorphism as well?
Sorry, what?
Isomorphism as well.
Well, just assistive algebra. Say, yeah. I mean, there is no notion of vertex, q vertex algebra.
This K0 is a vector space?
sorry, this is algebra because this is monoidal category. If you're not comfortable with it, then we can just tensor C. But yeah, I know this is a little bit mixed, but I'd like to say that if we just take this representation here, then the image can be understood as some contained in some ring of like something like this.
Like what you're saying is it does give a nice isomorphic in abstract tensor in C, but you still want to keep track of the integral structure?
Well, more precisely, I'm not really bothered with some field or integrality in this construction. I mean,
you might as well just tensor with C.
Yes, yeah, it's fine with if we test everything. Yes, right. Yeah. So this means that under this Q character, which is obtained by the composition of transfer matrix construction and the prepared realization, we obtain that these representations of quantum affine algebras or characters of quantum affine algebras can be understood as some fields of the something called q-deformed classical double algebras and vice versa. So this gives us a very, very useful perspective to both of these objects. So for one direction, let's say, we can use this representation theory of quantum affine algebras to understand or speculate the structure of these difficult q-deformed classical double algebras. I mean, this description by screening operators are not really useful when you really when you would like to understand some inner structure of this double algebra. And but anyway, so we can interpret this this field of q-deformed double algebras as some characters or representations of quantum affine algebra. So this means that this field, each field has some kind of structure which comes from the representations of quantum affine algebras. So for example, this suggests that we can some kind of consider some general tensor relations for double algebras using the representations of quantum affine algebras. For example, for generators, this from a representation theory of quantum affine algebra, we can expect that this q-deformed double algebra still has some kind of free generators, as in the non-deformed case, because this Grothendieck ring for the quantum affine algebra representations are also kind of some pivotable basis in terms of the fundamental representations of quantum affine algebra. Fundamental representations. So by pivotable basis, I mean that it has the Grothendieck ring has some basis obtained as ordered monomials with respect to these fundamental representations of quantum affine algebras. And this should play the role of the free generators of the Q-double algebras. And for the commutation relations or OPE, whatever, this should come from the tensor product structure of that representations of quantum affine algebra, or the product structure of this Grothendieck of representations of quantum algebra. Yeah, and at the time when Frank and Deformed developed this theory, this part was not at all understood, and actually it was quite opposite that they used, namely they used this realization as the q-double algebras to study this tensor product structure. But recently, I think we have a much more better understanding on this tensor product structure. So I think it is time to apply this tensor product structure to the q W-algebra side. And yeah, and again, in the opposite way, we can obtain new perspective on the representations of quantum affine algebra from q W-algebra. So this was main application of this identification. For example, this would give us some guiding principle to study or to develop this representation theory of quantum affine algebras. So for example, that this Grothendieck ring is described by the intersection of corners of screening operator, means that you can understand each representation as by first restricting to each rank 1 subalgebras. I mean, so looking into corner SI means restriction to rank 1 subalgebra UQSL2. Let's write it this way. And that it is exactly described as the intersection, means that it is enough to, it is enough to consider various restrictions to the rank 1 cases to understand this representation, at least at the character level. Yeah, and this means that, this gives us some way to manipulate this Grothendieck ring. For example, if you want to, for example, deform this Grothendieck ring for some reason, or if you want to, for example, do some Carsan-Lucid theory, then you might first try to deform again that q-deform screening operators, and this is indeed a very successful strategy, which is done by David Hernandez, for example. And even beyond that, by any algebraic manipulation on these pre-built algebras and screening operators would give you some kind of virtual Grothendieck ring. So even if it is not really some Grothendieck ring of some quantum affine algebras, you can do some or apply some intuitions from quantum affine algebras to study these intersections of corners of screening operators. Yeah, and that is recently intensively studied by, for example, Sejino. Yeah, and again, this by the transform matrix method, this gives us some many applications to integrable models, for example, or vice versa. Models or motivation. Yeah. So, for example, where you can. You can indeed prove that some famous relation in these integral models, which really holds in the Grothendieck ring using this identification. And probably the most important relation is something like T systems, or even more generally, some TQ systems, which are closely related to the cluster structure of this cluster algebra structure of that Grothendieck ring. Yes. So this Q character has been really extremely useful for the representation to investigate this tensor product structure of quantum affine algebras. And I want to stress again that this connection cannot be expected when Q equals 1, in this classical situation. So this is really a new phenomenon if you consider the Q analog. Okay, so, yeah, and just one remark briefly that, however, this algebra is still far from well understood. For example, we do not know some algebraic structures or axioms to really describe this calculus of Q fields. Like as I say, some kind of Q vertex algebras are not really well understood. Yeah. But still, there have some attempts to define these q-deformed algebras in different ways. So, for example, where these classical double algebras are originally defined in some DS reduction, And someone has tried to define this as a kind of difference analog of the DS reduction, for example. Yeah, and there is one participant who is working on this kind of difference analog of the DS reduction.
Here, let me ask you, this system is still, on the base of coding, code model, and it's quite different. You need obtain a two integral model, still you can, okay.
Where? Yes. Actually, my explanation for this part is a little bit misleading. I'm not sure whether this T system exists for this Gaussian model or XX. Oh,
I'm not sure, but I forgot. I asked you about it.
Yeah.
You mentioned about that.
Oh yeah, I'm not sure about Gaussian model. I mean, yeah, I haven't really considered this this model, so I'm not sure.
So RT, that's still previous algebra, associated you're talking about.
Sorry.
RT, that's the Q algebra, the Q-double algebra, still previous sense. You can talk about previous sense. In previous algebra sense, you can talking about the associated algebra you're talking.
Yeah, just associative algebra. Yes. All right. So this was a review in what was happening in 1990s, and now I would like to go to my more recent things or my research, which is still in progress. But I would like to tell you about some difficulties and ideas, which is just becomes available only in this recent 10 years. So yeah, so I would like to consider the super analogues of this theory. So I wrote here a problem because it is not a result right now, but yeah. So basically, I would like to obtain the super analog of this realization, where this is a mathematical physics conference, so I don't really need to justify why I'm interested in super, but let me just talk about one personal motivation to consider these super analogues or the representations of quantum affine superalgebras. So my main research project has been to construct so-called superduality for representations of quantum affine algebras or superalgebras. Which is jointly working with Jae-hoon Kwon in SNU and also Professor Masato Okado in Osaka Metropolitan University. So very briefly speaking, we have two categories that we would like to compare. So let me write this way. This is denoted by 1, and this is by 0. And this category is, in some sense, generated by representations which are constructed in a fermionic way. So more in mathematical terms, we use something like exterior powers, for example. So representation theoretically speaking, this fermionic construction usually leads to some finite dimensional representation. So this is usually finite dimensional representations of some quantum affine algebra or superalgebra. And on the other side, where this is fermionic, then this should be bosonic. So this is constructed from some bosonic representations. And this is usually infinite dimensional representations of, again, quantum affine algebra or superalgebra. But this algebra is usually also different from the one in here. And the idea to compare these two categories is to introduce corresponding module category for the quantum affine superalgebra. So this is certain module category. for quantum affine superalgebra. In this case, we always have super here. So depending on construction, these two algebras can be not non-super, but these should, when we interpolate these two, we always need these super things. So yeah, so there is a nice functor called truncation, which is exact and monoidal, and this can be and we found out that this this super duality was originally for to compare the BGG categories of classical Lie algebras or the superalgebras, but somehow we found out that this formalism also can be used to investigate the finite dimensional presentations of quantum affine algebras or superalgebras, level 0 more precisely. Yeah, and one more thing on super duality is that when rank of this quantum affine superalgebras goes infinity, then truncations become equivalence of category. So this kind of interpolation really works well of category. Well, and my question was that how this super duality appears at the Grothendieck ring level, and if this Grothendieck ring is also connected with some kind of QW algebras, then this super duality or this functor would give us some morphism between the QW algebras, or hopefully after taking the Q equals 1 limit. So that was my question, but after in the last year of my PhD student, I have some research on whether there is a result for the identification of this Grothendieck ring with some kind of QW algebras. But quite surprisingly, I cannot find any literature on that. I mean, this question might be very natural, right? So you just consider some superanalogue, which looks like some kind of problem that any PhD student who want to graduate can try. But for more than 20 years, there has been no results. So I wonder why. And here is some difficulties when you try to find some super analogues of this result. So yes. 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 This is it depends, but it is usually infinite dimensional. Yes, because it kind of contains this bosonic construction. So. Okay. Now difficulties. Well, basically the difficulty is that we really know nothing on this on both sides for this super analog. So for example, I mean, the problem is already appears when we try to formulate the correct conjecture for this kind of super analog. So the first problem is, what is Q deformed W super in this context? Well, so there is a notion of W superalgebra, WKGF, which is defined from Lie superalgebra G and some important elements. So you may just try to consider some Q deformation, right? But well, this is, well, maybe you can try to Q deformation, but even if before we take this Q deformation, you can see that this W superalgebras cannot be the answer, because before Q deformation, before Q analog, we may expect that, again, the critical center of this, for example, in type A case, this vertex, affine vertex superalgebra should be realized as some kind of W superalgebras. Let's omit this second one. But this cannot be true, because this is super, but this is not super. So already we lost the most, we lost some candidate to speculate what this center is. This is affine W-algebra corresponding to the SLMN. Yes. Yes, right. And even if you try to q-deform, okay. Oh, I didn't. Sorry. Yes. And then I would like this one. Yeah. Thanks. Yeah. I'm sorry. Right. Okay. And even if you try to q-deform this, yeah.
What does it mean, mass? So you mean, is it just associated without?
Yes. This is yes. I mean, yes. Well, this is basically in the affine vertex superalgebra. This is super, but if you take the center, then it is only even part. You do not have odd part here because center forces that the element here has weight 0 with respect to Cartan subalgebra. Then this should be even. And this vertex, this vertex algebra is kind of some kind of commutative algebra. So this, whether it is super or not is really important. I mean, you cannot say that this can be same as this with after forgetting supergrading. So this cannot be happening in this case. Yes, and for okay, sorry. And when you try to q-deform this algebra, you cannot really do not know how to do this because uniform definition. I mean, you can do some calculations for a smaller rank to try to consider some q-deformation of screening operators, but where if you try, for example, if you try to mimic the strategy of Frankel and Restikin, then you need some kind of q-deformation of Cartan matrix, like I said. But I don't know what is the correct definition of q-deformed Cartan matrix for supertype. I mean, there is a notion of Cartan matrix for super, but I'm not really sure what this q-deformation should be. And this is one. And another one is that, well, this is a problem at the double algebra side, but there is another problem at the quantum affine algebra side. That is UQ quantum affine algebra, super algebra is not at all well understood. So we do not really know some representation theory, and even more crucially, we do not know whether it has a universal R matrix or R matrix, like R matrix. So this is a very critical problem because that construction and also many studies on the representations of quantum affine superalgebras used this R matrix. So without this, we do not know really how to do this.
Do we know at least whether this K0 is a commutative weak?
I'm not sure. I mean,
that is not.
No, I don't think so. Yeah. I mean, even non-super case, the proof for this commutativity actually used some Q character. So yeah, I'm not sure, but yeah. So there are so many difficulties. So we do not really know what to prove to obtain this super analog. But yeah, but recently there has been some development on this W-algebra side. Okay.
Difficulty 2 is to UQ as it the super type.
Sorry. So this is quantum affine superalgebra. Yeah, I just read the type A case.
The case is simple type is you would get some problem on the construction of the universal algebra.
Yes. Yeah.
Is your point?
Yes. Yes. Right. Right. Yeah. It is what. Yeah, and here is some clues for type A case. Yeah, and from now on, I just consider the type A case, which means that we are considering UQSL and HEP. And yeah, and this comes from the new construction or realization of double algebra or free field realization. Let's say. Of WGLN. So this is a very famous result by Schiffman and Vasserot. Probably they did not put it in this form, but their results can be written in this way. So there is a notion of affine Yangian corresponding to GL1, H1, H2. It has 3 parameters with one relation actually. And there is a notion of also something called Fock space representation, which I wrote F3 with additional parameter called spectral parameter here. And we take some tensor product of n Fock space representation. So this is affine. Then this action can be actually I mean, the image of this algebra on this endomorphism ring of this space can be understood as a double algebra. So this means that this action vectors through the famous double algebra of GLN acting on this. Right? And this is also described by these screening operators. So this result, of course, comes from this is kind of a first step to construct the famous HT correspondence in a mathematical way. And again, this can be deformed. Now we use the Q1, Q2, Q3. Now we also use the GL1 het. And this is something called the quantum toroidal GL1. And again, we can consider the tensor product of Fock representations, but I here wrote 3. But there are actually 3 kinds of Fock space representations, 1 to 3, depending on which parameter you use to construct it, this representation. So we may consider more generally tensor products of these Fock space representations of any kind in any order, Gn or Un. Then the image of this quantum toroidal GL1 on this space actually is what is called q-deformation of Y algebra or corner vertex algebra. So this is Bernstein-Bacon version. Yeah. And this is not the end. And then in this context of quantum toroidal GL1, Bacon, Jimbo, Mukin, and with some other one, Berkovitsky. They introduced the notion of Q-Gartang matrix for supertype as we have desired of supertype. By computing the contractions between the so-called root current, contractions between root current, which comes from this quantum toroidal GL1 action on these Fock space representations. So this is a best generalization of the fact that the Cartan matrix Aij is actually obtained by the contraction of these simple roots. So there is a kind of notion of root currents that correspond to these simple roots. So you can define, in a sense, Q-Cartan matrix. And this is not all. They also introduced some algorithm that kind of I forget to mention that this is also described by some kernel of the screening operators. It's the right kind. Algorithm to compute fields in this q-deformed Y algebra. And this algorithm or this or results these fields in q-deformed Y algebras. And if you specialize suitably, you will get something called that should be called Q character of representations of quantum affine superalgebras in some easy case. So this means that there should be a connection between the Grothendieck ring for quantum affine superalgebra and this Q-deformed Y algebras, and when L equals 0. So when we only have two parameters here. Oh, and sorry, I forgot to mention that this L, M, and N counts the number of 1, 2, and 3 on this parameter. So this recovers when M equals 0. And this means that when only L equals 0 and M and N are not equal, then it would relate to some kind of super things. So this is the key result to obtain to speculate some correct conjecture. Yeah, and I think it's almost time, so I can just give you a conjecture. So let V be the let's say A natural representation or first fundamental representations of quantum affine superalgebra U cube S L M and head with spectral parameter A. And let's consider the category C, which is defined as the monoidal cell subcategory generated by natural representations with various spectral parameters, which looks like Q32I, and also it's dual. Then I would claim that the Grothendieck ring of this category is isomorphic to the q-deformed classical Y0 and N. Oh yes, yeah, and finally, I'm what I'm really working on right now is actually a kind of each aspects. I mean, and I'm indeed trying to prove this conjecture by constructing the corresponding transform matrix for super, where I told you that there is no universal I matrix for quantum affine superalgebras, but actually there is some kind of notion of generalized quantum group, which comes from some 3D integrability, so-called tetrahedron equation. So this is very interesting object. And this kind of explains some of these super phenomenon without having some superstructure, so that you can just apply many constructions on the non-super case, including this I matrix. So we can just do these constructions. Yeah, and also I'm considering some representation theory from this QY algebra perspective, partly with Ryo-Fujita type rims. And yeah, and finally, it is also natural to consider the Q equals 1 case, right? I just mentioned briefly here, but then that says that this should be classical, whatever it means, classical Y0Mn. And this is work in progress with Arim Song in the University of Denver. So I think I can stop here. Thank you very much for your attention.
When you consider GLN, you need affine GLN.
Yes. Yes. Yes.
You make the difference you need to make one still GL1.
I mean, that's a bit complicated. I mean, you know, actually this W algebra has another input. I mean, usually this W algebra is defined by real algebra and some nilpotent element, right? And this result actually gives us the principal W algebra, which corresponds to some nilpotent, which looks like this one. And if you use, I mean, so how to say? So if you use other toroidal like GL2 or GL3, then you will get some kind of box or rectangular type. I mean, this corresponds in terms of Young diagram, or if you see this as a Jordan block, then this corresponds to single row. And if you, for example, consider GL2, then this is expected to give something like this one, something like. And this is also for type A, and beyond type A, I cannot remember. I think there is some. No, this is all everything is type A here. Yeah, and type BCD would need another work. Yeah, but there is some people working on this. I mean, because this algebra, the affine Yangian of GL1 is also known as some kind of something called W1 plus infinity algebra, or and it's conjecturally. And to consider its type BCD analog has also some other motivation to kind of classifying these W algebras in terms of blocks. So in that sense, there is some work on type BCD.
Okay, can I? You have your conjecture. You have the okay, motivation of this section. Do you have some relation? Do you know the make some comment the relation between Grothendieck set and the Grothendieck set from your last result?
No, I mean this is the motivation to make me consider that problem. So this does not really help to make that statement. I mean, this is motivation for problems. But yeah. Rather, I would like to use that conjecture, or after I prove it, I would like to apply this to this picture.
The second step, you have the mention of the OD and the
yes.
Can you make also the beta and the interval model correspondence?
Oh.
Because I asked you about the necros, we know.
Yeah, but I know that I know the result what you mentioned, but that is kind of beyond my understanding. I mean, that is too physical for me right now. Yeah. Yes. But this result is really kind of motivated from the necklace of, for example, some QQ characters. Yes, right. Yes, it does. Yeah. And I would like to learn from you after the.
Say a little bit more about this QY algebras, like this corner inside what?
Now some q-deform screening operators, which is defined, of course, in a little bit different way.
It's a little confused. So you say intersection, it must be inside somewhere.
Yes. Yes. Again, I mean, I just written this, but you can also define this as a sub-algebra of some tensor product of q-deform Heisenberg algebras. or rank on algebras, I mean, and you can define some screen operators to define or realize this.
And what kind of object is that?
What kind? Well, at least right now it's just the associative algebra, but
I'm also confused about this like project, like it's classical. What does that mean?
classical. I mean, so let's say this side without becoming the zero. So this has 3 parameters, but actually they are connected by the sum of these are 0. So you only have 2 parameters, and this corresponds to that. Sorry, I'm a little bit, and also it has some scaling. So it essentially has 1 parameter, and that corresponds to the level of double algebra. And here we have 2, and we really have 2 parameter, and this is again Q and some level, whatever it means. And I like to consider some classical limit of this q-deformed Y-algebra, or before q-deformation.
When you say classical, like do you still have this Q Y algebra, but level infinity limit? Is that right?
Yeah, something like that. Yes, I mean, yeah. In this case, we do not have Q here because we are considering.
We know for fact somehow by definition that's a commutative algebra.
I mean, there is no definition actually. I have to find from the.
No, I mean like that one is defined, right?
Yes, that is defined, but
The limit is not.
yeah, I don't think so. Yeah.
So that's just a dream.
Yes. Yeah, hopefully.
In the last conjecture, you restricted to the case, so in Y are keep corner away, so there are 3 parameters, right?
Yes, that's right. Yes.
Why you can keep them, and there is still a proposed unit transformation. So then that would correspond to some representation. It's just more like a 3D, like more like a mathematical module rather than both module.
Yes, right.
I have a specific conjecture. I don't see any obstruction for generalizing the conjecture.
Yes, that's very good point. But the biggest reason is that just I'm not so expert on this vertex algebra, so I just begin from the easiest case. I mean, there is some, I mean, you can just add or subtract -1 simultaneously, right? I mean, so from that we can just make 1 0, for example, makes 0. So that was my just motivation. But yeah, probably we can do that for general case. I agree. But yeah, I'm not. Yes.
Yeah, although I don't know exactly what object to identify in the Grothendieck thing. Yeah, there is a
Yes.
in the general swing position.
Yes. Right. Yes.
But there should be some corresponding object.
Yes, I think so. But yeah, I don't really have no idea right now. Yeah, but that's a very good point. Thanks. Yes.
Any other questions? Let's thank the speaker again.